Alright, welcome back. Math1720. We are Chapter 8, Section 5, Polar Equations and Graphs. This stuff should be relatively familiar to us. We did this when we just did trigonometric. So magnitude, direction, alright, and then we did rectangular. So same kind of concepts here as we go through this, relatively a review. So if we look at the polar coordinate system, okay, it's going to be based on a point, and we call that the pole, all right, and it's a ray, and we call this the polar axis. All right, so we have a pole and a polar axis when we graph this. So it can be converted to rectangular. So if you guys remember back in Chapter 7, when we used the calculator to do our coordinate system, and it had like PR, P theta, PX, PY. Okay, it was just doing everything in polar. It was calling trigonometric in that section because we were dealing with vectors. Alright, but in this case we're still dealing with vectors, just kind of a different a way of what we're calling them. Okay, but we're going to do everything in terms of polar coordinates, which is no different than finding a magnitude and a direction. And we're still finding R and theta when we do these calculations. Okay, so if we take a look at this graph here, if R is greater than 0, point P lies on the terminal side of theta. The terminal side, not the initial side, right? If R is less than 0, the magnitude less than 0, then the point P lies on the ray pointing in the opposite direction. Alright, so that's really no different than what we did before. When we had a vector, and we had like U or we had minus U, same concept here. Alright, so polar positive is going to be pointing in the upper coordinates and negative is going to be in the lower coordinates. So this is a polar graph that you see here. Alright, it has magnitudes and it has thetas. What I really want you to start thinking of is something like longitude and latitude. If you look, down on the earth, that's really what we're talking about, and that's why we use polar coordinates. This is more towards GPS type scenarios and things like that when we use them. Okay, this is no different than what we did in Chapter 7. So every polar coordinate has a horizontal component and a vertical component. So this should be relatively just review for us. So X is our horizontal component, Y is our vertical component, so X is going to equal R cosine theta, Y equals R sine theta. Okay, and conversely, we're able to go the other direction. The magnitude is still R squared equals X squared plus Y squared, or R is the square root of X squared plus Y squared. Okay, and then we want to find the angle theta. It is our vertical over our horizontal. So we would do tangent inverse of Y over X to get angle theta. Just note here, X cannot be 0 because of division by 0. Alright, so let's plot each point here, and we have polar coordinates. Then, once we plot the point, we're going to find the rectangular coordinates. Make sure that your calculator is in degrees mode when we do this. Okay, so if R equals 2, that's our magnitude, and theta equals 30, we're going to graph this from the x-axis, which is the initial side, up to the terminal side, 30 degrees. So we can see where the 30-degree angle lies. Okay, and then we draw the magnitude of 2. Notice it lies on one of, I'm going to call the latitude lines from the Earth type of scenario there. Okay, so we can look at how the polar coordinates, are just circles with radiuses at 1, 2, 3, 4, 5. That's really what the magnitude is going to be. It's going to be a radius of our polar coordinate. Okay, so there's how we would graph this polarly. We have a magnitude of 2, and we would be at 30 degrees. Okay, you guys should be able to do the rectangular piece. It's going to be 2 cosine of 30 and 2 sine of 30 when we do this. Okay, so X, right, 2 sine of 30, 2 cosine of 30. Alright, cosine of 30 is square root of 3 over 2 times 2, ends up giving us square root of 3. Alright, and then Y equals R sine theta. So you have 2 times 1/2 equals 1, because sine of 30 is 1/2. We've been doing that all year long. Okay, so that's our rectangular coordinates. Would be square root of 3, comma 1. Okay, so all relatively just, kind of review, other than the polar graph. All right, but everything else we did in chapter 7. All right, so now we have something. We have point Q here. Okay, and it is in what? Radians this time. Okay, so we got to be able to do both. Okay, so if we're going to graph this, okay, the magnitude is -4, so we can see that Q is at -4, so we're going to be going down. Okay, and where does that lie? Well, it's on the 1, 2, 3, the 4th ring. Okay, since it's going down, and then it's at the angle of 2 pi over 3. Okay, hopefully that makes sense there. So, if we look at 2 pi over 3, technically it's where? Okay, it's showing positively in the second quadrant. But since our magnitude is -4, we would draw it in the opposite direction there. Okay, so it's 4 units in the opposite direction from the pole on the extension of the 2 pi over 3. Okay, so 2 pi over 3 lies in the second quadrant, but since the magnitude is -4, we're going in the opposite direction of where Q is located. So please make sure that you note that, because that line can go in both directions. Alright, so to find the x, okay, it's going to be -4 cosine of 2 pi over 3. If you don't know the fractional piece, that's fine. Use your calculator. Make sure that you are in radians mode when you do this calculation. So change the mode in your calculator for this one. Okay, and then the y component is going to be -4 sine of 2 pi over 3. Alright, and when you do that, you end up getting -2 root 3. Okay, so fairly straightforward on those. This one was more, challenging understanding the graph. Alright, moving forward here. Say we have R. This one again is in radians. So our magnitude is 5, and our theta is -pi over 4. So we're going to see how this changes the location of the graph based on the angle and having a positive magnitude. So think about it. What does the negative angle mean, and what's the positive magnitude going to do when we draw out the sketch of the graph? Okay, so the theta is negative, the angle is going to be in the clockwise direction, so we're going to fall from the x-axis, we're going to fall from 0, -pi over 4. Okay, and then the magnitude is 5, so we put it on the 5th ring. Okay, taking a look, we want to calculate the x coordinate, or the horizontal component. It's going to be 5 cosine of -pi over 4. You end up getting 5 square roots of 2 over 2. Alright, you can get the decimal in your calculator as well. Just remember, you leave your calculator in radians mode for this one. And then we have to find the horizontal component, so it's going to be y equals 5 sine of -pi over 4. Alright, and we get 5 sine of 7 pi over 4. So where's the 7 pi over 4 come from? Remember, the -pi over 4 is what puts us in the 4th quadrant. The 7th pi over 4 actually puts us in the 4th quadrant, but in a positive manner. Okay, so the rectangular coordinates for this one come out to 5 square roots of 2 over 2 and -5 square roots of 2 over 2 when we do this calculation. Okay, so just a brief note here. It says, well, given point in a plane can have only one pair of rectangular coordinates, the same point can have an infinite number of pairs of polar coordinates. Okay, so it has to be a function, essentially, one pair of rectangular coordinates, but why can we do infinite polar coordinates? Because remember, we can keep going 360 degrees in either direction. Okay, so we can keep going in a circle over and over and over and over. That circle can only match that specific rectangular coordinate. Alright, so how will we do this one? Alright, it says give 3 other pairs of polar coordinates for the point P, okay, with the magnitude of 3 and a direction of 140 degrees. Well, I would, look for your answer choices on your homework. You're going to be able to add 360, subtract 360, add 720, subtract 720. Alright, so if you can remember back to like chapter 2, we talked about coterminal angles. That's really all this comes down to, is where those lies. So here's some examples here. When we do this, we have 3 pairs of polar coordinates for this point. We have 3, 140. Then we have 3, negative 220. We have negative 3, 320. And negative 340. All terminating in the same polar coordinate. Okay, so you are able to what? Change the magnitudes and change the angles. So, if we look at the first one, we have 3, negative 220. Well, what does that really mean? That's doing what? 360 with the 140. So we're just going the other way, negative 220 degrees, and the magnitude's positive, so it ends up at the same point. The negative 3, 320, okay, we're going in a positive manner, okay, to get there, but we're changing the opposite of it. So if we go 320 degrees, that still puts us in the 4th quadrant, but the negative 3 on the magnitude actually tells us that we are pointing into the 2nd quadrant. Okay, and then we have negative 3, negative 40. So what does that do for us? Alright, we're going negative 40 down from the x-axis, and then we're going to go in the opposite direction, which makes us point into the 2nd quadrant when we do this calculation. Okay, so there's multiple ways of doing this. Alright, because you have a negative and a positive angle that you can do the opposite magnitudes on. Okay, and then you have multiple positive angles that you can just keep the same magnitude on. So a couple different ways of getting there. Alright, so let's determine 2 pairs of polar coordinates for the point with the rectangular coordinates negative 1, 1. Alright, well guys, this is where we have to go the opposite direction now. We have to come up with the polar coordinate first. Okay, so if we remember that, we have to find the magnitude and we have to find the direction here. So remember, the magnitude is going to be the square root of x squared plus y squared. Okay, and the theta we're looking for is tangent inverse of 1 divided by negative 1, right? Our vertical over our horizontal. So we can substitute those in. Alright, so the point in rectangular lies in negative 1, 1. Alright, but we have to have the magnitude and the direction here, and we have to do those conversions. Okay, so tangent inverse of 1 over negative 1 gives us 135 degrees, so that puts us in the 2nd quadrant. And then we have to do negative 1 squared plus 1 squared. That gives us the square root of 2, which is our magnitude. Okay, so now we want to find 2 other pairs of coordinates that terminate in the same location. Okay, so we found the solution of where we want to end. We want to end at square root of 2, 135. Now we want to find some other possible coordinates that get us there. Okay, so one way is we can do square root of 2, 135, that's the original one, and the other one would be if we went 315, okay, that puts us 180 degrees off, but then if we put it as a negative magnitude, we're going to have negative square root of 2, so it will still point in the same direction. Okay, so that's how we work through those. Alright, so let's talk about graphing polars of equation, or I can't speak, sorry about that, polar equations. and we are going to do it in polar form. So we're going to define the polar equation of a line. AX plus BY equals C. That's just the definition, the standard form of a line. Okay, you might have just only learned it as Y equals MX plus B, or those sort of things. So AX plus BY equals C. So what are we going to do? We're going to convert that. We need to find what the XR is and the Y is. Okay, and that's if we're given something in polar. So we would go R cosine theta to get the X, and we would go R sine theta to get the Y. So we got to do that conversion first. All right, and then we can factor out our magnitude R. Okay, and then R would be C divided by A cosine of theta plus B sine theta. So this is if we were to take our polar equation and convert it into a linear equation, or vice versa. Okay, if we have our linear equation, we're going to convert it into a polar equation. Okay. All right, so we're going to define the polar equation of a circle, and that's what it comes from, right? You should remember that it should be x squared plus y squared equals the radius squared. Okay, but in this case we're going to use a squared so we don't get confused with the radius and the magnitude and that sort of thing. Alright, so starting off with the equation of a circle, x squared plus y squared equals a squared. We know that we can replace x squared plus y squared with r squared. Okay, that's the Pythagorean theorem, but that's how we calculate the magnitude. Okay, so we know that r ends up being plus or minus a. When we get r equals plus or minus a, it gives us the general form for the polar equation of a circle. Okay, so the linear equation for the circle is the x squared plus y squared, okay, equals a squared. Okay, the polar coordinate, or the polar equation, is plus or minus a. Alright, so let's do an example here. For each rectangular equation, we're going to do a couple of these. Okay, give the equivalent polar equation and sketch its graph. This is probably as challenging as this unit's going to get in this section here. Alright, we're going to start off with y equals x minus 3. So our first step is to get y and x on one side of the equation, and then we have to rewrite y and x in terms of its polar. So the x has to translate to r cosine theta, the y has to translate to r sine of theta. Okay, so when we rewrite this, we're going to write it as x minus y equals 3 because that puts it in the ax plus by equals c form that we're looking for. We replace x with r cosine theta and y with r sine of theta, and we factor out r to get the magnitude, and r is going to be 3 divided by cosine of theta minus sine of theta. So essentially we just found the polar equation that matches the linear equation y equals x minus 3. We converted it to polar in case we wanted to graph it. So the equivalency y equals x minus 3 is the same thing in polar as r equals 3 divided by cosine of theta minus sine of theta. Alright, so how would we graph that? Well, you get to graph this in your calculator. When we graph it, you can kind of see how the polar graph on the left equates to the graph on your calculator. So when you graph in your calculator, you're going to have to hit the mode button and go down to polar coordinates. Alright, so you're going to get out of Cartesian and you're going to go down and you're going to select polar coordinates. So the way you do that is if you hit mode, and I'm on a TI-84 Plus, but if I hit mode and I go down, and normally function is highlighted, but you should see func, F-U-N-C, you should see P-A-R, P-O-L, and S-E-Q. You need to move your cursor over to P-O-L. Alright, and hit enter. Now you're going to put it in polar. So when you do that, notice when you hit y equals now, it's actually r equals, just like that you can see on the screen here. When we're in r equals, we're graphing in polar mode. Alright, so let's do this next example here. We have x squared plus y squared equals 4. So hopefully remember a good way to replace that one, okay? So it's not quite as challenging for you. Remember that r squared equals x squared plus y squared, okay? So that's essentially just r squared equals 4, and we square root both sides. The square root of r squared is r, and the square root of 4 is 2. So that's how we get the graph of a circle that has a center at the origin, which is 0, 0, and has a radius of 2. Okay, so that's essentially how that breaks down. Very, very simple in this scenario. So what you're always, don't screw up, always recognize if you see x squared plus y squared, that's automatically just going to be r squared. Okay, whereas the other example we had to, put it in a linear form and replace the x with r cosine theta and the y with r sine theta. Okay, so if we just take a quick glance here, it's possible for the magnitude to be less than 0, but the graph of r equal 2 and the graph of r equal negative 2 coincide. It's pretty much the same thing, okay? Just the direction changes. So if you graph this on your calculator, okay, you should get the circle shown here on the right. Alright, just so we do this one together, alright, make sure you hit mode, put your calculator in polar. You're going to hit y equals, so you're going to, and then you're going to hit 2. Okay, and then I just hit zoom 6, zoom standard, and it essentially puts that on the model for me. Okay, there's not a zoom polar button, but you should be able to graph this and get a circle that has a radius of 2. So there's how we graph in polar on our calculator. Alright, better good way to get a circle. Just because it's a lot harder for you to graph this in your standard linear form, right? To graph a circle from before, you would have had to use, see the rectangular formula of x squared plus y squared equals 4. To graph this, you would have had to solve for y equals before. So when you did that, you would have had to do plus or minus the square root of 4 minus x squared. And the plus would give you the top half of the circle, the minus piece would give you the bottom half of the circle. But when you're actually in polar coordinates, you can graph the circle in its entirety. Okay, so we can graph this. Okay, we're going to go through some special named graphs here. When we do this, they become kind of fundamental in calculus and things like that later on. So if we want to graph r equals 1 plus cosine theta, this gives us a cardioid. That word should make sense to you once you see the graph and take a look at this. Okay, so you can do some ordered pairs here to find the graph. Okay, I don't know, this is more of an old school method, check out all the different degrees, or just put it in your calculator and take a look at it. Okay, the reason it's called a cardioid is because it represents your heart, essentially, or it's a graphical depiction of a heart in essence. So you can take a look and see how that graph of 1 plus cosine of theta, okay, is graphed on your calculator. And you can do this, on a polar grid. Okay, here's how you do it. Alright, so you change your graphing interval. So you're still in polar and you're still in degrees. Okay, and then you go and hit window and you change your theta min, theta max, your step. Make sure that your window matches the window you see on the screen. Okay, and the screen on the right, that's just if you keep going down to change your scale. So when you have your window set as such, your graph should match what's on the screen. Alright, so let's graph the next one here. We have r equals 3 cosine of 2 theta. This is not like the errors on the homework assignment. This is not cosine squared theta. This is cosine quantity 2 theta. So the 2 theta is the argument here. Now what graph are we going to graph here? We're going to graph the rows. Okay, so this is an equation for graphing the rows. And once again, you can create a bunch of test points, okay, or just go into your calculator and graph it. So these are kind of cool. I would do these as you guys go through the lecture and see that you get them. Okay, so this is how you graph rows in your calculator. Okay, and why don't you play with some of the values and see what happens. Oh, sorry, I hit the wrong button there. See how this is r equals 3 cosine of 2 theta? Play around with some of those values and see what changes. Look at this graph. Where's the 3? What's the significance of the 3 here, and how does it affect the rows? What's the 2 theta doing? How does it affect the rows? Maybe do a 3 theta, maybe do a 4 theta. Play around with this and see what your different graphs look like as you guys plot some of these famous graphs. Okay? Let's look at this one. We have the graph of r squared equals cosine of 2 theta. Remember that once again, this is just cosine of the quantity of 2 theta, so the parentheses should go around 2 theta. This is not like the homework glitch that has cosine squared written out as such. Okay, so you have to graph plus or minus the square root of cosine of 2 theta, because this is given to us as r squared, so we have to solve for r when we do this. All right, you can come up with a complete table and test points, or put it into your calculator and make sure you adjust your window so that it fits. So this is what we call a lemniscate. A lemniscate, okay? Pretty much an infinity symbol. So if you take a look at this, you know, what is the 2 changing the 2 do to the theta, and those sort of things. What happens if there's a value in front of cosine? So play around with these graphs a little bit and check them out. So it's really just kind of cool to mess around with and look at them. A good window for your viewing, okay? You just got to kind of pick it and mess around with it. Notice the window in this screen, okay? The min and max values on the theta and the r. Alright, but remember, when you have to graph this in your calculator, you cannot do plus or minus. You have to do the positive version. So you would do the positive square root of cosine of 2 theta, and then the negative square root cosine of 2 theta. Because remember, when we square a root, r squared, we get plus or minus when we take the square root. So there's 2 possible solutions, and this is the only way for your calculator to graph the whole thing. If you forgot and didn't do the negative, you would only have one of these showing on your screen. Okay, so we want to graph r equals 2 theta, just 2 theta alone. This is called the spiral of Archimedes. Another cool thing, side note, you should check out what an Archimedes cup is. I would Google that and see what an Archimedes cup is. Pretty cool little thing here. But if we go ahead and graph r equals 2 theta, you're going to get what we call the spiral of Archimedes. Okay? Don't bother doing all the guess and checks. I want you guys to get to the graphs and take a look at them. But this is what the spiral of Archimedes does. And if you keep zooming out, all right, the graph does keep going on. So it's the spiral of Archimedes. Archimedes was an ancient Greek guy that did a lot of math stuff. But once again, do look up what an Archimedes cup is. It's pretty cool. Notice that we're plotting this one in radians now, and not degrees. So you can still do polar coordinates, right, in radians. So make sure that you're paying attention to what the question asks for, if you need to be in degrees or in radians when we do this. Okay? Alright, let's go back the other way. Say now, before I've given you stuff in rectangular, right, and you had to solve for r and put it into polar. Now we have polar, and you need to be able to go to rectangular coordinates and graph it rectangularly. Okay, so we're just going the other direction now when we do this problem. Okay, so we're going to start. We have r equals 4 divided by 1 plus sine of theta. We have to get everything in the numerator, so we're going to multiply both sides by 1 plus sine theta. We are just doing basic algebra skills here, okay? Because we need to solve for, sine theta is going to give us a clue in this one. All right, so we end up with r plus r sine theta is equal to 4. Okay, and then we have to replace r. This is very, very, very important. Notice what's in red is r sine theta. We automatically know that we can replace r sine theta with a y. Had that said r cosine of theta, you would have replaced it with an x. We also can replace r with square root of x squared plus y squared. Okay, so you got to look for substitutions. It's a little bit more tricky going from rectangular, or going from polar back to rectangular. You're going to have to always look for r cosine thetas, r sine of thetas, and r's. Those are really just what we're replacing. Okay, so then we're going to go ahead and do some algebra here. And so that we can solve, we're going to move the y to the other side. So it ends up giving us the square root of x squared plus y squared equals 4 minus y. And then what do you think we got to do to both sides to get rid of that square root? All right, we're going to square both sides. So we're left with x squared plus y squared is equal to the quantity of 4 minus y squared. Okay. Then if we FOIL that out, we have to, or expand it. All right. So remember, 4 minus y is quantity squared. Means I'm going to take 4 minus y times 4 minus y. So use your box method or your FOIL method to solve for that. Okay? Then next, we're going to put it into like a linear type equation for us. Okay? We can move the y squared to the other side and they cancel because I have a positive y squared on both sides. When I move one over, it cancels. Okay? And then we can term it in terms of x squared. So this is just our rectangular equation right here. We have x squared equals 8 times y minus 2. We factored out a negative 8 from the negative 8y plus 16. Okay, so now we can graph that equation. Okay, we have x squared equals negative 8y minus 2. It might be easier for you instead of saying x squared, okay, because that's not a common way for us to graph it. If I step back here, you could have solved that for y. We could have done x squared minus 16 divided by negative 8. Same exact thing. So that's solve that equation for y if you need to and graph it. You're going to get an upside down parabola. Okay, and notice the graph on the left is if we graphed it in rectangular form. Okay, and the graph on the right is if we graphed it in polar form. And notice the rectangular form matches the polar form. It should, okay, if you do everything correctly. All right, so how do we want to classify polar equations? So the biggest way we take a look at the classification here. Okay, the first two on the left we classify them as circles. So we have r equals a cosine of theta. Okay, notice that one ends up in quadrants 1 and 4, and we are splitting across the x-axis. Okay, r equals a sine of theta. Okay, we're in the first and second quadrant, splitting the y-axis. That should make sense, right? Cosine's a horizontal component, so that circle is going to sit on the horizontal axis. Sine is a vertical component, so r equals a sine theta should sit on the vertical axis because it's dealing with sine. Okay, and then the last two on the right, those are lemniscates. Okay, so it just depends on if we have one in terms of cosine. Notice once again the one in terms of cosine resides on the horizontal axis. Okay, and the one with sine it's in the vertical quadrants, but that's on the diagonal. Okay, I get that it's not 100% on the y-axis, but we can kind of see how that relates. Okay, so those are the basic forms for a couple circles and a couple lemniscates that we're working with. All right, moving on here. So if we look at this, okay, we have limicons, okay, our Archimedes circle stuff. Here's the equations for those. R equals A plus or minus B sine theta, or R equals A plus or minus B cosine theta. And then we can look, if the ratio of A over B is less than 1, we're going to get the 1 on the far left hand side. Okay, if the ratio of A over B is 1, we get the cardioid. Okay, and then if A over B is between 1 and 2, you can see what's going on. And then what happens if A or B is greater than 2? Well, why do we talk about 1 and 2 and things like that? It has to do with, kind of outside the realm of cosine and sine in the domain and range. Okay, so let's take a look at Rhodes curves here. What happened when you change the n? All right, I asked you guys to kind of do that before when we were messing around with the Rhodes curve. So we can see and change the number of leaves. If n is even, okay, we get what we have on the left hand side. We have A sine n theta, A cosine n theta. But if n is even, okay, we're going to get an even number of leaves on the rows. If n is odd, we're going to get an odd number of leaves on the rows. Okay, so that's just some ways that we classify polar equations. All right, this stuff should probably mostly all be new to you. Okay, but it's not too hard. The hardest part is going back from polar back to rectangular. I think that's where you might have some struggles, or ask me some questions in class, or let me know if you need a Zoom or team meet, or those sort of things. But all right, guys, one step closer to the end of class here. But like usual, email me with any questions, or let me know if you got to meet. Else, I will see you guys in class.